Session we start with Kartik Waghmare from ETH Zürich, and he will talk about proper scoring rules, estimation and forecast evaluation. Please.
Thank you very much. It's very nice to be here. Yesterday, a lot of people said in their talks that there's a talk tomorrow on proper scoring rules. If I'm not mistaken, this is it. If I am mistaken, that's also very nice. I'd love to check out this talk that everyone's looking forward to. It's also on the same topic. So this talk is based on a review paper, which is already on archive. It has the same title that I've written with my supervisor, Professor Johanna Ziegel at ETH. The paper will appear sometime next year in the annual reviews of statistics. In this talk, I'll mostly try to focus on the estimation part. If you want to read up more, and also more on what I'm going to talk about here, more background, more detail, also more accuracy, you can look it up in the paper. But I'll try to focus on what I think are the most interesting developments on this topic in the last few years. So what are proper scoring rules? Most likely you have had some education in statistics. You already know what maximum likelihood is. Basically, the idea is that if you want to fit a probability distribution to some data, what you do is you calculate that number there, the sum of logs of the probability density evaluated at your observations, and you find the p which maximizes that. This is equivalent. You can think of this as empirical risk minimization with that loss. It's a very particular function of the probability distribution that you're looking at. So it's one of these rules that we use to fit probability distributions to data. It turns out this is not the only rule that you can use. It's just one very special member of a large class of loss functions that you can use for fitting probability distributions. This family is what we call proper scoring rules. The origin of this concept comes from very practical ends. Around the 1950s, Americans, they had computers and they were really interested in predicting weather. The problem of putting a probability estimate to the chance of rain tomorrow instead of just putting a word to it, such as fair chance or probably, that's what gave rise to this discipline. So the problem is quite simple, right? You want to come up with the probability for the chance for the event. Say it will rain tomorrow, or it could be a real valued event. You want to know how much it might rain tomorrow, so it will be a probability distribution on the real line, or positive real line, since there can't be negative rain. So they came up with a lot of methods to evaluate these predictions, calibration diagrams and as such. So there are quite a lot of methods, and the problem is if you want to compare two different, say, methods of producing these predictions, using these multiple metrics kind of confusing, right? So you want a one-number summary that can summarize the performance of a particular method or algorithm, or even a person. So you just want a one-number summary for that performance. It turns out this can be conceptualized quite easily. You come up with a loss function S, which takes in your probability estimate p hat and the observation that you observe the next day. And what you do is you average this over multiple observations, multiple predictions, and that sort of describes the performance of your method. The problem they realized was that coming up with such a loss function S is a delicate matter. It's quite non-trivial. If you don't do it right, such summaries can be very gameable, in that you can produce methods which have very nice scores, very nice performance according to these summaries, but they are not good predictions at all. So this problem was considered by this American meteorologist, Glenn Breyer, and he came up with the first proper scoring rules. The general definition came a bit later from this computer scientist called John C. McCarthy. This is the general definition. So let's say Y is a set. Y is typically, it's the space in which you want to make in which your event lies, right? So if you're interested in the quantity of rainfall, Y would be R, and if you are interested in whether it will rain or not, that would be 1 or 0. So then that would be your Y. And P is the set of probability measures on Y, usually a convex set. You don't admit all probability measures possible. Often there is some structure, right? So P is some convex set of measures, and what you do is you use this shorthand S of PQ, which is the expectation of S in that way, okay? And proper scoring rules, a scoring rule S is said to be proper if this condition is satisfied. So if Q, the truth, lies in the argument of this expectation. It's called strictly proper if the truth is the only probability measure that minimizes your risk in this way. You can contrast this with the concept of consistency that we often see in statistics. So what S is here is really an M estimator, right? You have a loss, and what you want to do is find a P which minimizes that average. This is called an M estimator, this of P. And an M estimator would be consistent if with infinite number of samples, as the number of samples increases, you converge to the truth. Proper scoring rules are really a population counterpart of this statement. So what you do is you replace that sample average with an expectation, and that's the definition of a strictly proper scoring rule. Now, this is quite a strange, well, not strange, but weak thing to say, right? It's sort of linear in Q and has this relationship with the maximum. Doesn't really tell you much. So you might wonder, what does it actually mean? So John C. McCarthy and later Tillman Knighting and Adrian Raftery, they showed that any such proper scoring rule, any such function, it has to be of this form. This is basically a order 1 Taylor expansion of the function h. And h can be any concave function on the space of probability measures that you're looking at. In addition to, so we call this h entropy, and it behaves pretty much like the concept from physics that you're familiar with. It's very high, very negative for measures which are very pointy. A point measure, often the entropy is not defined, but it's technically minus infinity. And it's kind of, you want to have estimates with higher entropy. They are more spread out. So yeah, so we define these two numbers, the entropy and the divergence. The divergence is really like the equivalent of distance in this case. It really characterizes or describes the geometry that the scoring rule S imposes on the probability measures that you're looking at. I'll talk more about what this actually means. So we have these two numbers, and they will come into play later. Nice thing about the divergence D is that if you were to minimize S, it will go to some minimum you don't know, but if you were to, it's equivalent to minimizing D, and that basically, if you were to minimize D, that can only go to 0, right? It has to be positive. So that's the difference.
What is that in a product? Does it assume...
This is actually an integral of this function, which is actually a subgradient or supergradient, supergradient. So it's actually a function of y and p, where y is a point. And what you do is you take the integral of that function on these measures. I shortened things up here, but it kind of delivers the idea that it's an order 1 Taylor expansion, basically. But it's a well-defined numerical thing. You can calculate it.
It requires the gradient with respect to P of H. It
Yes.
itself is in the space. It's called tangent space topology.
That's right. So you have to, it's what you call a Gatto derivative, quite a kind of functional analytic definition of a derivative, but it can be calculated, so there's no need to worry. This is a very general characterization of most general possible characterization of proper scoring rules. You want to come up with the proper scoring rules, just take your favorite concave function on the space of measures and calculate its order 1 Taylor expansion. That's a proper scoring rule. And this is true for every proper scoring rule, that there is an entropy that gives rise to it. So before I move on, I'd like to tell you the one other aspect in which proper scoring rules are just, you can't escape them. They are the foundation of a very basic statistical problem that you encounter all the time. And that problem is conditional distribution estimation. So let's say you have two jointly distributed random variables x and y, and you want to find out the conditional distribution of y given a particular value of x. How do you do it? Well, this is the recipe. You have to calculate the argument of that. And it's both ways. So any function that works for all such joint distributions that gives you conditional distributions has to be a proper squaring roots or equivalent to one. So it's both way calculations. There's no escaping that. So just to summarize, just as when you want to do conditional mean regression, you minimize the L2 loss in this way. You minimize the proper squaring rule loss when you want to do conditional distribution regression. It gives you the whole distribution. This is not a, so that was what I said. And this similarity it's quite uncanny. It's not an accident. Proper squaring rules are in many ways very similar to what you expect for L2 loss. So just as you see, that's a L2 loss for R1, but if you had Rn, that would be the Euclidean metric, and it has a nice Pythagoras theorem, right? A similar Pythagoras theorem exists for proper squaring rules, or at least the divergence. On top of that, just like you have a bias variance decomposition for this L2 loss, there is a similar decomposition for proper squaring rules, all of them. You can look them up in my paper. Going deep into that, it's probably not worth the time. So now I told you that there is the maximum likelihood, and classical statisticians would tell us that this is all you need. You work with a standard probability distribution. It gives you beautiful closed form estimates for your parameters, which are also asymptotically optimal. So why do you need all these extra proper scoring rules? It turns out modern statistical applications require, they don't satisfy these nice assumptions that maximum likelihood or the logarithmic score, as I said before, require you to make. So take, for example, this particular way of parameterizing a probability distribution. Eta theta, if it's linear in theta, that's an exponential family that we are all familiar with. I have nice statistical theory around it. If you were to do maximum likelihood, this is what you would do. No problem with that. Usually C theta can be evaluated in closed form, so there's no problem. What if, however, you're interested in doing something modern? You are dealing with high dimensions, probability distributions on images, for all you know. Now you don't actually believe that the neural network, one of the neural networks, it's the true generator of your data set. In fact, that's nonsense, right? So in a sense, that basically says your model is misspecified, which means that maximum likelihood doesn't deliver the optimal asymptotically optimal estimates that it does in theory. On top of it, if your model is non-standard, you can't evaluate C theta easily. So you're going to have to compute it numerically, which is quite a lot of work just for evaluating your loss once at one point. So basically, maximum likelihood becomes unviable for these modern applications. So that's not what we do with these days. What we do is called score matching, and the thing is to notice that once I know eta of theta there, the normalizing constant is basically redundant, right? So maybe there is a loss function which doesn't rely on the computation of that normalizing constant. Turns out that's true. You can try to do something like this, and that actually boils down to using a scoring rule now known as the Heverian scoring rule. It doesn't depend on the normalizing constant. It lets you fit probability distributions without having to bother with normalizing them. So that kind of lets you do estimation, and we call it score matching because of that score. Contrast this with Langevin dynamics, which lets you simulate from a distribution without, even if it's not normalized. So together, it's basically, so you can estimate a probability distribution without having to bother with normalizing constants and draw from one, simulate one. It's quite a happy marriage, right? And one of the triumphs of this beautiful marriage is generative diffusion models. A lot of new advancements in this area, they come from that paper, which basically put these two things together. And I guess I don't need to comment on the success of these methods. Something similar can be done for discrete distributions. You can use pseudo-spherical scoring rules, which have the same property, that you don't need to bother with normalizing. A different way of Yeah, so there's one other way I'd like to illustrate how other property scoring rules can be obviously useful. To do that, I need to tell you what these kernel scoring rules are. So what they do, what they are basically you take a symmetric function h, we call it conditionally negative definite. It's very well studied objects in analysis. You don't need to understand the nitty-gritty of that definition. How we define a kernel scoring rule is this. It's basically a quadratic in P, and h is sort of the kernel that you're using to evaluate it. It's really a quadratic in P, and that's the important thing to keep in mind. Now, a lot of modern applications, they rely on what we call generative modeling. And previously we used to call them structural equation models. And basically the idea is that sometimes describing a probability distribution using a density is just a lot of work, can't be done, just a bad idea. So what you do is you say that I'm going to tell you how to draw from this distribution instead. So in this way, my random variable y, instead of giving you the density of p theta, I tell you that there is a function g theta, and what you can do is draw from a standard normal distribution, put it in that function, and that's how you can simulate from y. Some of you, I think, are actually working on something like this. So this is quite common, for example, weather prediction, right? You put in the distribution of, say, temperatures and rainfall for today, and you run a very complicated ensemble, and it spits out some numbers for you in the end. Now, fitting this using maximum likelihood is a very bad idea for multiple different reasons. One thing is, well, you can try to work out your probability density, right, using these multidimensional transformation formulas that we all learned in probability. So that would be the formula. It has a inverse there, and a Jacobian, and a determinant. All of these are bad ideas, and what maximum likelihood requires you to do is do all of them for every single evaluation of your loss function. So many different reasons to try, but if instead you can, if you use kernel scores, so let's say this is my kernel score, h is the kernel I've chosen, then it turns out you can do this in a much more painless manner. So you just put y as g theta of n. Okay, now I have some complicated expectations to evaluate, except I know how to simulate g theta of n, so what I'm going to do is just do that instead. I'm going to replace those expectations with these sample averages and painlessly calculate my loss. Very flexible way of fitting those kind of distributions. And if you are working in a conditional setting, and there was a covariate x, something similar can be done. Just replace those things with this guy, and yeah. So it's quite an old idea, but it's coming back for some reason. So yeah. So here are some examples of kernel scoring rules that you might have seen before. This is kernel maximum mean discrepancy. Usually the kernel we choose here is this Gaussian or Laplacian, very successful in two-sample testing. In fact, I think still to date, the state-of-the-art results for two-sample testing, they are using this metric. It's not exactly related to proper scoring rules, but you can motivate it that way, and also for training GANs. That's one of the so training GANs used to be a very difficult problem because of this min-max formulations that people used to rely on, this adversarial. But with this, you can do it painlessly again. But all that aside, arguably the most famous kernel scoring rule is the CRPS, widely and wildly popular in meteorology and hydrology. As of this morning, there are at least 20,000 papers on using CRPS, at least mentioning it. So at least some of them must use it in good capacity. And there's the energy score, which is the multidimensional counterpart of the CRPS. A bit more, actually, there's this power beta. So this is the example of kernel scoring rules you can use. You can also write them as expectations, no big deal there. And well, these were the two examples I gave you about how nicer or different proper scoring rules can be used for more nicer kind of modeling perspective. They can also be used in different ways. For example, there's this paper by Schorer and Hamill, which actually designs a proper scoring rules which is tuned, it's sort of designed to capture a certain kind of behavior in your probability distributions. In that case, it was this kind of correlational structure for some multivariate distributions, which the other scoring rules couldn't perceive very well. You can also go the other way around. You can sort of dampen or numb your proper scoring rule to certain aspects of the distribution that you're not interested in. And then there are also weighted scoring rules that a lot of people talked about yesterday, two very nice talks. So this is for the kind of classic setting in which, say, you are doing classification, 0, 1, say the patient has cancer, patient doesn't have cancer. Now, false positives and false negatives have wildly different implications, right? So you would like your inferential procedure to take this into account, but doing this is actually a delicate matter. Without, you want to do this while preserving the fact that your rule is consistent, it's a proper scoring. So there's quite some literature on the topic. What I'll do next, and I have 8 minutes, or 3 minutes.
Like 6 minutes.
Okay.
Because you get
Okay, yeah, thanks. So what I'll do now is try to talk about some of the new results in the paper, which put a few things in perspective. So kernel scoring rules, I introduced them to you in a very abstract way before. They were, as a quadratic in P. Turns out there's a much nicer way of thinking about them, which is as basically distances between probability probability distributions. So what you can do is, whatever kernel you choose, turns out a Hilbert space corresponding to it, and what the kernel scoring rule does essentially is that it takes your measure and it maps it to a vector in that Hilbert space, and just the kernel scoring rule is basically the distance between these two measures in that Hilbert space. Between these two vectors in that Hilbert space. A bit abstract, but still, it's a distance after all, which helps. It's also symmetric. It treats essentially your model measure and your observation measure in a symmetric way. Those are the same thing. It doesn't care. This is quite a nice property to have. A lot of people want it. It turns out that under certain mild conditions, not universal conditions, but under certain mild conditions, kernel scoring rules are the only proper scoring rules with this nice property. And that condition is this, that you have to admit point measures into your convex set. So long as you admit what we call these ensemble predictions, or basically point measures as into your model space, then it turns out that the divergence of a proper scoring rule is symmetric if and only if that proper scoring rule is essentially a kernel scoring rule. Quite interesting. A lot of people didn't know that, so it was very nice to know. What I'll do next is now show you that. So that kind of is an argument for using kernel scoring rules, assuming you want symmetry, right? But in practice, we don't just use any kernel scoring rules. There are certain kernel scoring rules which are way more popular. Case in point, CRPS. So how do you explain, what is the good reason for using these loss functions in particular instead of just any kernel?
Could I go back to the previous slide?
Sure.
Is it significant that it's a Hilbert space and not a Planet space? Are you using RKHS connection or something?
I think it is, yeah. There is this, it has to be a Hilbert space. I mean, there just is. Using this conditioning negative definite kernel, there corresponds a positive definite kernel, which corresponds to its RKHS. But it's an interesting question, actually. If you can use a Banach space, that would correspond to like some kind of dual metric, and yeah, but it won't be a proper scoring rule. I mean, because this has to be. It's an interesting question. I can't comment though. Not the spur of the moment. Okay, so why is CRPS nice? I sometimes ask one of my colleagues why he thinks CRPS is nice, and all he replies to me is that, oh, CRPS is just nice. So what is the reason? And what I'll try to do now is try to convince you that under certain nice assumptions, CRPS is the way to go. There is no other option. So let's look at this nice property, which is translation invariance. So which basically says that if you were to move your probability measure and your point by a certain fixed distance, the score doesn't change. Basically tells you that the score doesn't care, doesn't attest particular significance to particular parts of the domain. Everything is the same to it. It's sort of kind of invariance. So what that implies is that the kernel you use for your kernel scoring rule has to be stationary. It has to be of this form. This can be exploited to come up with a spectral representation for your kernel scoring rule. Basically, it tells you that any such translation invariant kernel scoring rule has this form. Essentially, what it's doing is that it's comparing the characteristic functions of your measures according to a certain L2 metric. The measure of that L2 metric is the spectral measure of the kernel. It's coming from the kernel. And also looking at the means. So it's like sum of two distances, which is fine. But in practice, we often need a little bit more. For example, there's this concept of homogeneity. So let's say you are a meteorologist and you're working with someone from across the Atlantic, and you like kilometers while they like miles. Now, you want to use a scoring rule which doesn't, require you to choose one of these metrics. Homogeneity lets you do that. Basically tells you that if you were to put in your data in miles, you'll get your predictions in miles, and if you were to put it in kilometers, you'll get them in kilometers. This is not a trivial condition. It's quite strong. It has strong implications. It's not true for any kernel scoring rule. Definitely not true for Gaussian or Laplacian kernels that we saw before. And there is also for multidimensional ones, you have the concept of isotropy, which is that if I was to, rotate everything by a fixed matrix, fixed rotation, the score shouldn't change. So it turns out, if you require your scoring rules to satisfy these, okay, we'll skip on this part. So it turns out that if you require your kernel scoring rules to satisfy some of these invariances, then that essentially just determines which kernel you're talking about. In particular, for CRPS, it's the only one homogeneous translation invariant kernel score there is. So if you want your proper scoring rule on real line, let's say you're dealing with real predictions, then if you wanted to have this symmetric property and on top of it translation invariance and on top of it homogeneity, just to maintain friendship with your American friends, then you have to use CRPS. And something similar is true for energy scores. So yeah, it's quite nice results. Basically tell us, kind of point to a broader question of where do the loss functions we use in practice come from? What are the reasons why we use them? And what are the nice mathematical properties that lead us to use them, that make them so practical and useful? Thank you very much for your attention, and yeah, fire away your questions.
Yes, thank you. And now it's time for questions. Are there any questions?
Yes?
I think occasionally you see this kind of pseudo-justification for scoring rules that if you're eliciting forecasts, you'll get, you encourage honesty in all of the people giving it to you. But, often you're not expecting, if I'm using this proper scoring rule, I'm not expecting to get the true probability measure. So we're in you mentioned misspecification. I was wondering, similar to Bayesian asymptotics, is there any results on if we're considering a class of misspecified models, what the proper scoring rule, what is the minimizer of the proper scoring rule across that class of functions, and whether that is still something we would want to give?
That's a good question. Misspecification, I did talk about misspecification for maximum likelihood, but similar concept is there for proper scoring rules. The thing is, though, that the probability measure space, like these, the model space for a lot of these proper scoring rules, they're just very large, so you don't have to worry about misspecification, right? So you take, for example, a kernel scoring rule, very large, dense family. So I wonder what's the point. But for particular ones, like say, what is a good example here? Say the score matching loss. Yeah, that's also, it's worth studying, but maybe not for kernel scoring rules. I would probably have to think about this before giving a good answer. Any more questions? That's all? Okay, cool.
We have time after the break to ask a quick questions. Okay? Thank you, Kartik.